So today we commence with the derivation of area formulas. And as I said previously, by derivation we mean simply a proof, but these proofs will be partly algebraic in nature, so derivation does seem a good word. But again, the point is this: just like with the proof, we attempt to explain these formulas. So the hope is that for each of the derivations that we do, by the time we are done, you will understand clearly why it is that the formula is correct. Now, I know that you have encountered some or all of the area formulas of the chapter at some time in the past. Teachers have given them to you, probably without much attempt to justify them. And this might have created the illusion in you that you actually understand them, that you really know them, but I suspect that you don't. And I wish actually that I had a button that I could press, like in Men in Black, that would just like wipe your memory and you would have no knowledge of area formulas, perhaps even be surprised that they're possible. So attempt to do that as best you can. Attempt to wipe from your memory any knowledge that you think you have of area formulas. And today what we'll do is this: we'll consider rectangular area. And we will get a formula for that. So here it is, a rectangle that's A by B. That is A one direction, B the other direction, or if you like, that's the length of the pair of adjacent sides. And we will use the cross symbol, the X symbol, to designate that. You see it there. So when you see that symbol, don't read that as multiplication. Read that as simply, that's how it is that we give dimensions. This is a rectangle that measures A by B. That is A one direction, B another direction. Now, there might well be multiplication involved in the formula, but we haven't said that yet. Okay, so how will we derive the area formula for a rectangle? Okay, well, here's how we'll do it. We'll start with the A by B rectangle. You see that in figure 1, region 1, that I have labeled. And what we'll do is this, is we'll attach to it an A by A square and a B by B square. So we attached an A by A square, and we attached a B by B square. And then let us finish this figure out so that what results is a new larger square. And to do that, we must attach another A by B rectangle, which you see is region 4. Okay. So what have we done again? We started with region 1, which was the original A by B rectangle, and we have supplemented it with two squares, one A by A, the other B by B, and then another A by B rectangle to produce a rectangle. Now, I won't go through all the details of this to prove that this actually is a square. I think you'll find it quite plausible that this is possible to do. So, now here's what we will do. We will compute the area of this figure that results, this A by B square, in two distinct ways. One way, we will ignore the interior complexity and only consider its side length. The other way, we will treat it as a sum of subregions. Now, this strategy is common throughout the chapter, and it's also common in other areas of mathematics as well. That is, where we have a certain geometrical or mathematical and general object in front of us, and we're able to model that in more than one way. But since it is the same object, we are able to say at the end that whatever conclusions we reach from one model and from the other model, they must be ultimately the same, right? That is, we can, in this case, put an equal sign in between them. Let me show you what I mean. Okay, so let's just treat this as a big square and not worry for a moment about what's on the interior. Well, it's a square of side length A plus B. And the square area postulate says that to get the area of such a square, we square the side length. And as we have discussed a number of times, the quantity A plus B squared becomes A squared plus 2AB plus B squared. Now, let us model the area of this square in a second way. Let's add up the areas of the subregions. Now, as for subregions 1 and 4, at this moment in time, we don't have like a formula that would give us the areas of these. This is just the original A by B rectangle twice over. So the best that we can do is this. Let's represent the area of that simply by the variable A, okay? Or the unknown would be better to say A. So if we're going to sum up then the areas of all the subregions, we have double the area of the rectangle, and then, we have an A by A square. We know what its area is. That's A squared. That's the square area postulate. And we also have a square of side length B, which is B squared. And notice that we did make use of the area addition postulate in this. Oh, and notice that we also did make use of the area congruence postulate as well, because the two rectangles present in the diagram are obviously congruent to one another. And then we concluded that their areas must be equal. So I don't expect you on the worksheet to actually write all of this out, but just do note that the postulates from section 1 do actually operate in the background. All right, what then are we able to do? What we're able to do is this, is we're able to equate these two expressions. Oops, that's supposed to be a square there. We're able to equate these two expressions. That is, a plus b quantity squared is 2a plus a squared plus b squared. And again, the a plus b quantity squared is a squared plus 2ab plus b squared. And that is twice the area of the rectangle plus the area of the a squared plus the area of the b squared. And then just algebra. Derivations, as I said, are awfully strongly algebraic in flavor, so let's do the algebra. So after I subtract an a squared and a b squared, I get 2ab is equal to twice the area of the rectangle. And then I suspect you've seen what I'm about to do, divide both sides by 2. And then I get the area of the rectangle is a times b. And let us pause to contemplate that for just a moment, okay? The capital A, our unknown, represents the area of the rectangle, for which initially we did not have a formula. But we have now discovered that that area must be the product of a pair of adjacent side lengths, its dimensions, if you like. That is, it must be the product of side length A times side length B. And that then is an area formula, okay? You've probably seen this as perhaps length times width, which is fine. We will typically instead call it the product of a pair of adjacent sides. But that's it. That's the derivation. So we have now gone from square area, together with the other postulates, to rectangle area. And then next, in the next section, will come parallelogram area, which we will derive from rectangle area. And then once we have parallelogram area, we're able to derive on its basis triangle area. And then we're able to build the other area formulas on the basis of triangle area. So this is, like so much else that we do, like a pyramid. We have a foundation, which are the postulates, and then we derive out of that. It's like a sort of a pyramid where the tip is the same size as the base. We sort of go straight up, as it were. We start with square area, and then from that we have rectangle area, and then from that we have parallelogram area, and then from that we have triangle area, and that will be the work for most of the rest of the chapter.